Hey guys, it's time to continue our learning at home adventure. This week you had radioactivity and fission and fusion in your Edgenuity lessons. So my video is going to go over those. I'm going to start with radioactivity. So let's go ahead and go there. All right, radioactivity. So before I can get into that, we need to review the basic structure of an atom. So you guys have been learning this for a long time now. An atom consists of 3 subatomic particles. We have protons, which are positive, electrons, which are negative, and neutrons, which are neutral. The protons and neutrons can be found in the nucleus, that center area there. And then the electrons are found on the outside in the electron cloud. This is not a very realistic depiction of an atom, but this is fine for our purposes. Now, atoms can be stable or they can be unstable. So remember, the nucleus is made up of protons, which are positive, and neutrons, which are neutral. Well, when you have more than one proton, you have 2 or more positive charges. And you hopefully remember that positive charges repel other positive charges. So the protons in the nucleus are constantly pushing apart. Well, thankfully, there is a force holding them together, which is good because we need atoms for you and I to exist. This force is the strong nuclear force. So that is what holds the nucleus together and keeps atoms together. So the strong nuclear force allows atoms to remain without the protons flying apart. Now, as you have more and more protons, you have a stronger and stronger force trying to push it apart. So you need more and more and more neutrons to balance this out. Now, it's not just a 1-to-1 ratio. You can't just say, well, I have 20 protons, I just need 20 neutrons. As you have more protons, you actually need more and more and more neutrons. This is the neutron-proton ratio is what tells you how many neutrons you need for a stable atom. So the neutron-proton ratio is a very important measurement that gives you an idea of how stable a nucleus will be. If you have too many or too few protons, then the atom is going to decay to reach a stable state. It'll either undergo alpha decay or beta decay. It just depends on what the atom happens to need. So let's talk about those types of decay. We have alpha, beta, and gamma. So alpha decay is when it's literally going to give off a helium nucleus. It's going to give off 2 protons and 2 neutrons. So mass is going to be lost, and it's going to become a new element. So it's lost protons, element is changing. Now an alpha particle, which is the helium nucleus here, is really large. And since it's so large, it's actually really easy to block it with like weak materials like paper. So paper could protect you from alpha radiation. Now, it's still bad if you're exposed to it, but you only need something relatively common like paper or plastic or something to protect you from it. Beta radiation is going to have a little bit more kick to it. So beta radiation, instead of being a helium nucleus, it's going to be an electron or a positron, which is the antimatter version of an electron. So electrons are negative, positrons are positive because they're antimatter, so they're the opposite of matter. Once again, it's going to change the element, but now the mass of the thing isn't changing. So you're going to lose an electron. Electrons are going to have a little bit more energy to them. So you're going to require something like metal foil or plastic or something to block it, not just paper. So beta, still dangerous, but still relatively easy to protect yourself from. Gamma, on the other hand, gamma is high energy photons. Photons are light. So you have this high energy light particle that's being released, and this is going to have enough energy to very damage living tissue. And it's much harder to block. So you're going to need something like lead to protect yourself from gamma radiation. Best idea with gamma is just to stay away from it. So speaking of damaging tissue, non-ionizing radiation is low enough to not harm living tissue. But all these decays that we're talking about here are examples of ionizing radiation. They have enough energy to damage living tissue, so therefore they're harmful to us. Now, there are ways to protect yourself from it. Here's an example of an X-ray procedure. So you can see the technician is wearing this vest. This vest is most likely lined with a material like lead, and that material will protect them from any radiation they may encounter. So you can wear a protective vest, protective gear of any kind, like there's the patient might be wearing an apron that has the same material. As you can also see that they're not just taking a whole X-ray of this person's body. They're being very careful to only expose the area necessary for the X-ray. So another way to protect yourself is to only expose a small area. And then third, when they take an X-ray, it's not this continuous X-ray beam being shot out. It's a quick snapshot. It's a small burst of radiation. So you minimize the amount of radiation, the area you're exposing, and you wear protective gear. So there are ways to protect ourselves from these types of radiations. Now, this whole thing we've been talking about is the decay of radioactive material. Now, how quickly it decays depends on something called the half-life. Half-life is the amount of time required for the amount of a substance to decay by 50%. So this depends on the material. If something has a half-life of 10 years, that means after 10 years, 50% of it will have decayed. And 50% of it will still remain in the original unstable form. Look at this table right here. So starting at the top, if 0 half-lives have elapsed, then you still have 100% of the material. Once 1 half-life progresses, you've lost half of that material. So I went from 100% to 50%. Every half-life is going to decay 50% of what you have. So right now we have 50% of what we started with. Another half-life goes by, so I'm going to lose half of what I have. Well, I already have 50%. So I'm going to lose half of 50%. So I lose 25%. Every half-life is going to take half of what you have. You don't go 50% each time. Every single time cuts what you have left in half. So you go 100%, 50%, 25%, 12.5%, and so on. This pattern right here will fit every element. The only difference is the amount of time that it takes per half-life. Some materials go really, really fast. Other materials take millions of years. It just depends. Now let's move to fission and fusion. So fission and fusion are the nuclear processes that are used to generate energy, or nuclear weapons. We'll start with fission. So fission is a process that splits a large nucleus into 2 smaller ones. So fission is splitting. Nuclear refers to the nucleus. So the name literally means nucleus splitting. And remember, the nuclei is being held together by the strong nuclear force. So since there's a strong force holding them together, when you rip that apart, all that energy is going to be released. And that's why they produce so much energy, are such devastating weapons, because of all that energy that's being held inside that is now released. Now the basic process, so you can initiate fission by bombarding large radioactive nuclei, such as uranium, with neutrons. So if you have these fast neutrons going through radioactive material like uranium, the neutron is going to be able to strike one of those big nuclei. The reason you want big nuclei is because they're easy to hit, unlike small nuclei. So the big one is going to be hit by a neutron, and when it absorbs it, it's going to split. And when it splits, all that energy is going to be released, and it releases 2 smaller nuclei. So I started off with big uranium, and now I have 2 smaller ones. Now remember, they're not going to be uranium anymore. They will be 2 smaller elements. They will be different elements. So you split uranium into 2 different elements. And when you did that, you also will produce energy and more neutrons. The other neutrons that you produce are going to go find more uranium, strike them, and split them. This is called a chain reaction. Since you started one process, it's going to keep going. More neutrons are going to be released, splitting more uranium, causing more of a reaction. More and more energy is going to be released. Now, this process is something that we are able to start and control relatively well. So Nuclear power plants use this process. We are able to start it, we are able to stop it, control the speed of the reaction, and generate the energy that we want to generate from it without catastrophic effects. Obviously, there have been disasters like Chernobyl and Fukushima, but relatively nuclear power is pretty safe. Now, the energy produced by nuclear plants does have several advantages. It has relatively low pollution and emissions produced. So compared to coal plants, natural gas, the pollution produced by nuclear plants is really negligible. So looking at this, when you see these pictures of nuclear plants, it looks like they're giving off a lot of smoke. This is actually water vapor. So these are cooling towers, and this is just water vapor coming out of those towers. This isn't smoke, it's not billowing pollutants in the air. This is actually better for the environment than a coal plant that's billowing out chimneys of black smoke. And not only do they produce relatively low pollution while they're running, but they produce tremendous amounts of power relative to their footprint and the fuel they're consuming. Now, clearly, their fuel has the radioactive byproducts, which is a problem of itself. But as far as the pollutants generated, so the carbon dioxide, the greenhouse gases, that is much lower than traditional fossil fuels. Fusion is a very different process. So fission is splitting. Fusion is literally the opposite, putting together. So this is a process that combines two small nuclei into a larger one. So you're fusing two small things into one bigger thing. So the basic process, we have two hydrogens here. It can be other elements, but hydrogens form the basis of the most common form of fusion out there. So we have hydrogen 2, which can be called deuterium, and hydrogen 3, which can be called tritium. Well, when they fuse together, they're going to produce a helium nucleus, a neutron, and if you were to take the mass of those two things, these two have less mass than those two did. So that means some mass was lost during this process. Well, matter can't be created or destroyed. So what happens is that mass is going to become energy. And that lost energy is going to be tremendous. So this is going to be a huge amount of nuclear energy that's produced during this process. So this conversion of mass to energy is what makes nuclear fusion so powerful. So this is something that Einstein predicted. His most famous equation, E equals mc squared, tells you that energy and mass are equivalent to each other. All the energy in the universe comes from mass. When you eat, you are taking mass into your body and converting it into energy. So mass and energy are interchangeable. This is how nuclear processes work. They take mass and they turn it into energy. Now, this process is incredibly difficult. It is not something that we easily achieve on Earth. Have we ever done fusion? Yes. Is it an easy process to do? No. Is it a process that we have been able to generate energy efficiently from? No. So it takes so much energy to actually start and control fusion on Earth that it's not actually viable for energy production yet. It takes more energy to do than it releases right now. So for now, fusion is relegated to stars. Things like the sun, this is their energy production method. They are fusing billions of tons of hydrogen in their cores every second. Tons and tons of fusion bombs basically going off inside the sun every second. And this requires huge amounts of pressure and temperature. The temperature of our sun's core is about 15 million Kelvin. And the amount of pressure is like about 250 billion times the atmosphere of the Earth. The pressure is huge, the temperature is huge. We can't easily recreate those conditions, so fusion is difficult for us right now. So for now, fusion generated power is out of our reach, but we're working on it. This would clearly be the next big change in human energy production. And that's all I got for radioactivity, fission, and fusion. Remember, only the stuff that is in this video and on that slideshow are the things that'll be on the quiz. If there's something I didn't cover here, but was in Edgenuity, it's not going to be on the quiz. So definitely watch this and then go do that practice on Edgenuity. If you have any questions, please let me know. I'll be doing office hours on Thursday. If you have pop in and want to ask your question, then I'll post your quiz tomorrow. Be sure to like and subscribe, and I will see you in the next one.